Well, good morning. Thank you for your time today. Thank you to Datamine for organising what I'm sure is going to be a very valuable event, and is proven to be so. As the introduction, which I wrote, as you can hear, and my title slide quite clearly suggests, my name is Mark Roux, and I'm a passionate resource geologist currently working for Goldfields. I have the particular privilege of working with a team, some of them in this room today, of supporting 4 world-class gold operations across various technical aspects. Whether it be resource modeling, geological modeling, complex and simple, we as a team always try and strive to investigate and implement solutions that are both practical and sustainable. Among those, and the basis of my talk today, is the determination of dilution in open pit mining. And as my fantastically uninspiring title suggests, I'll be using the MineScope Optimizer tool currently available within the Datamine suite to do so. It's an obligatory forward-looking statement for everyone to take in. And with that. But before I jump into the body of my talk today, I'd like to just spend a couple of moments just setting the scene. A lot of mining companies around the world tend to rely on global or general dilution assumptions when it comes to incorporating dilution in their open pit operations. And while this practice is by no means incorrect, if I may, for a moment, just echo a 2013 white paper, which is authored by SRK's Ibrahimi on the matter. And he makes the following very interesting statements. While we do our best to identify and calculate all other cost items of a project, no matter how small, it is common to make general assumptions about dilution instead of quantifying it. And this is usually due to insufficient budget, time for studies, and also lack of a well-defined methodology. Furthermore, he proceeds this by saying that mining dilution is one of the most important factors impacting the economics of a mining project. Now, it's difficult to argue against this, and while the global assumptions which often are applied to these open pit mining operations are based on valid and true data, there are obvious major failings in ability to incorporate any short-scale or accommodate any short-scale dilution changes. And while I'm aware that the severity of not incorporating these short-scale changes will impact different ore body geometries differently, I'm also equally of the opinion that no matter what ore body you have, having the ability to accommodate for some short-scale dilution in your model will not only impact the positive impact of the economics of your project, but also the selectivity of your material in the mine itself. Now, MineScope Optimizer offers a sustainable option for us to accommodate this local dilution, and this will be the focus of our journey together today. A little bit of theory. Dilution, simply put, refers to waste material that is not separated from ore and is set mined with ore, resulting in an increase in tonnage and a decrease in grade. So there's generally 2 major defined categories that we split the dilution into. The first being this internal dilution. This is really a dilution that we choose to take. And that might be for a number of reasons, one of which that material within the ore block is too small or too discontinuous to discriminate it out, or we choose to take it because it makes more sense from a mining efficiency point of view to include it. Mario Rossi, in his 2009 paper in the APCOM conference, which is entitled Counting for Dilution in Resource Estimation, he correctly refers to this type of dilution as a change of support. Or in our context, we can refer to it as a change of selectivity. I'll get back to this comment and this subject in the next slide. The second type is what we refer to as the external dilution. This is really the waste dilution, the edge of the ore block. It occurs as a result of the precision inability of our equipment to be able to dig against a line. So total dilution is therefore defined as a combination of both this internal and external dilution. Simple. I want to focus for a moment on the context of selectivity change, because I'm pretty sure that there's a couple of geostatisticians in the room that are starting to get a bit uncomfortable with what I'm about to say. But what I want to say is that it is a key principle in considering dilution in open pit mining. The reason I say that is while the equipment parameters that we apply, which is based on the equipment you use, such as minimum mining width, if you will, or this external dilution, while these parameters are indeed constant, the result that they impact upon your ore body is not. And the reason for this is that there is a inherent non-stationarity in both the geology and mineralization across any ore body anywhere in the world. So because of this, and while the dilution is defined by these practical limitations, you need to be able to incorporate these 3 points. Number 1, how is the block laid out? B, how we mine against those blocks, and C, how the mineralization behavior changes across it. It's therefore important that, and the reason I'm advocating for the consideration of local dilution where possible. If you look at that image on the right, for instance, you can see that's a typical big block layout, which is effectively what we're trying to produce when we run this MSO process. And what you can see is that across the same grade bins, you're seeing quite a variation in the support. And that's really what I'm talking about. What you're extracting, using to extract those blocks is not changing. The equipment stays exactly the same. The reason they are changing the geometry is because there is a difference in the mineralization behavior on a local basis. So the next few slides are going to illustrate this local versus global dilemma through a couple of, through an example which is clear and very embarrassingly simple, but it's good to show a couple of things. Let's consider the following setting. We have an economic mineralization, which is flanked by waste. Let's define a static minimum mining width, which incorporates portions of waste, as you can see. And let's make the assumption that portion that we're extracting between the dotted blue lines is still economic. The tail package is economic. If there is an assumption that there's a total 20% dilution through that ore package, you can see through this very simple example how the local dilution departs quite quickly away at all points of that dilution in terms of local versus global. This example really shows the value of being able to define this local dilution. Not only does it give you an idea of where your local dilution changes, but what's important is additional information it tells you on a local scale can lead you to ask and gather other information. For example, if you look at that 40% dilution in the middle, yes, it's telling you that your ore body is incorporating 40% dilution, but it's also telling you that your mineralization is thinning quite dramatically there. So there's information that you can gain from that, but it's telling you about the local geological setting that may be important in considering future updates or future settings of this particular ore body. And this is one of the reasons why the team at Goldfields and myself have been working on trying to incorporate a process which can capture this local dilution effectively. And that is what we have been able to successfully do using MSO. So the value of getting local, in summary, and ultimately preserves the short-scale variability of the ore body. That's what we're trying to do. It also provides increased resolution in other reconciliation data sets, so we can monitor things like internal dilution or external dilution on a local basis as well. As I've touched on before, it allows that sort of proactive approach to what happens when there's a big short-scale jump in dilution that tells us a bit more about the mineralization type that we can then take and impart back to the geological models and say, oh, we've seen something else here. It's just another level of resolution that we can use to inform our models. And finally, it also helps us refine and define the overall global dilution. At the end of the day, we can derive a global dilution, but we're now using a local process to help define and refine that. Onto the actual process, it's remarkably simple in MSO, and there's only a couple of key inputs that we need to consider. The aim is to apply sort of a practical mining parameters, ultimately as I've explained before, to the resource model or the undiluted model to produce and replicate how we would extract it. So we're trying to replicate things like the dig design and how you would dig against it. Ultimately, I like to refer to this as a local change of support against these parameters. Because what you're seeing is there is a change in the variable, as I can remind you back to that photograph that I had before of the dig outline, you're seeing that variable change in the local support of what you're actually extracting. So the 3 simple inputs in terms of the MSO itself are the cutoff grade, the minimum mining width, and the external dilution. The cutoff grade, what I like to say is if you're going to, in this particular process, we guide ourselves against the actual production. So if you, in this case, have a layout where you are putting your grades in 3 particular grade bins, high grade, moderate grade, low grade, then use that in the MSO process. And you would run your process from high grade to low grade, which is what you would try and do, because you would obviously try and honor that high grade, high value material more obviously. The second parameter which I explained to you is pretty self-explanatory, the min and mining width, and this is guided by the equipment constraints and say the resource model cell block dimension. Now MSO, this is applied to the what we call the variable direction. We only have the option to apply one variable direction in MSO, and so this is the one we would apply it to. So it gives you a minimum mining width, but you also can dictate to how large you want that that direction to continue optimizing towards. So you can put an upper limit to that as well, and that should be dictated against what you expect to be able to mine or what the the ultimate large big block size would be in your pit, and of course the external dilution. And this is guided by a minimum mining width down complexity selection. A lot of people refer to this dilution as skin dilution. Other processes have applied it. And you obviously got to look at your equipment relative to your deposit to see how well it can be against it. And you can run sensitivities against this. You can go half a meter, whatever you might see, and see the differences that you might come up with. But yeah, so those are the three general inputs that you'd have. There's a couple of other supporting inputs that you would use to tweak the ultimate result, but these are the major areas that you want to concentrate on when you set up the process. So in the next sequence of slides, I'm going to run through a process of an actual area that we've run this on, one of our deposits, and just show you how the inputs and outputs look. So in the first run, we look at the first grade run, which is the input model on the left-hand side is our resource model, or should we call it our undiluted model at this point. Our first level is to run the high grade position, and that's obviously selecting the high grade cutoff grade for the first run. We then input our min mining width and external dilutions. And what we do is we let it run, and it generates a set of MSO shapes. And these MSO shapes obviously represent the parameters we've put in there, but obviously they optimize against the cutoff grade we've designed. And that's really the output that you end up getting. You sort of get if you want a footprint of where the optimized cutoff grade MSOs for this cutoff grade would lay themselves in this particular example. It's pretty good. So I've still got the superimposed undiluted grade below the MSO outlines there. And if I zoom in on one particular area, what I'm showing you here, obviously again as I stated before, that's the undiluted grade below the MSO output. What you can see there is that external dilution that's been incorporated as a result of the skin that we've applied in this particular case. I think it was a half a meter. And this is what's good about this process, because it allows you to use the local, and this is where it really has its advantages over global dilution. It uses the local blocks around it to dilute it, that particular grade block or that particular MSO shape that is optimized. So in reality, this is replicating exactly what you would be diluting on a local basis, and that's what we like. That's what I like about this particular process. So once you've generated that first set of output shapes, you then would apply your diluted grade across those. So basically, it takes those shapes and provides an average, and you get your first change of support against that cutoff grade. You move on to the next grade. In this particular example, I've gone with the 3 grade for an example to explain it. So the next grade is your moderate grade. And it too uses the input of the undiluted model. But in this case, there's a functionality in the MSO to exclude the blocks which have optimized in the previous blocks. Obviously, you don't want to consider the same blocks again. So what it does is it gives you the remnant of what hasn't optimized as your input. You then put the same process together, without the same parameter together, with one exception. Obviously, the cutoff grade is now at the lower position, and you generate the same set of shapes. And there you go, the second set of shapes which represent this particular cutoff grade. In the inset here, what I've shown is the scenario where you have previously optimized void. It's called void, the high grade model, which is next to a new optimized grade for the moderate grade. What I'm showing you there is that it obviously doesn't dilute on the left-hand side because it doesn't have any material. It's something, the assumption is you've actually dug it out. It's replicating again what you're trying to do in reality, and it places dilution only on the area that is adjacent to a portion that hasn't been extracted by the previous grade then that was applied for the MSO prior to this. And then, of course, there we have the final diluted result for this particular grade bin, and you can see again the second level of selectivity change in support. Then we go on to the third and final run for this particular example. Obviously, there's not much material left because we've optimized the majority of that volume with the previous 2 runs, but we're at the lower grade, so we take what's left. We run our outlines, we produce our remnant outlines on that, and then we run the average of those. So the combination of all these are then added together quite simply, a couple of macros, put it together, and you're able to have a look at the results. So that's our input, which is our undiluted model, and you can see the level of selectivity reduces visually when we have reduced our output model. That's the final diluted model for the same area. What I like to see here is that we have applied this dilution. We've applied parameters that are real, that we believe we're going to extract against, and we're trying to replicate how this is going to look in reality and how it's going to behave in reality. But you can also see it still does where it can. It tries to maintain blocks at different support sizes, and you're getting different volumes of high grade still coming through there. And that's really how you would try and lay it out in reality. And that's what we try to, and have successfully been able to produce using this particular process. And if you look at the, this is just a great tonnage curve showing the results of those 2 model examples, the blue being the undiluted grade, and the red being the diluted equivalent. I've got the position of a particular cutoff grade, and you can see the diluted equivalent has dropped the grade and increased the tonnage as expected for this particular example. So in a number of quick steps, I have illustrated a method using this MSO process, which can quickly and effectively model local dilution into our model. So in summary, today's presentation has shown that there is some clear advantage supporting the application of MSO in our open pit dilution. First of all, it is easy to set up, it's repeatable and it's auditable. It generates these XML files. Anybody's used, I'm sure there are a lot of people who use the MSO, it generates XML files which you can obviously review and you can upload for future runs. You can test it against different parts of the ore bodies as well, see how it does. But perhaps what I like the most about this, and this is what really sets it apart for me, is that it allows the mineralization and equipment configuration to dictate the dilution locally. And we're not assuming what a dilution would be. We're saying this is what how we intend to mine it with this equipment. This is what the model's mineralization looks like, and it goes and runs the process and dictates that dilution locally. There are other advantages, and you can, as I've explained before, you can dynamically model things like external dilution and internal dilution and other parameters. There's also real-time reconciliation, which we do, and we do this quite a lot to ensure that we get in our parameters right. So if you've got your as mines, for instance, you can actually take your as mine and compare it against this diluted model and see just how close you are getting to how you believe you would be extracting, how you actually extract it, and if there's some adjustments in the parameters that need to be made. That's a practical and clear selectivity adjustment. That's ultimately what we are producing, as I've said before. And it's really it actually adds a lot of transparency, I believe, in quantifying our dilution more effectively in open pit mining. And overall, it's going to have a positive impact on your mineral economics and of your local mining predictability. And that, ladies and gentlemen, in the room and online, that's the basis of my talk today. And there's some of the acknowledgements to the references. I also want to acknowledge the Goldfields team who have helped design this, not least of which is Sean Hackett, who may or may not be online today. He's been very, very helpful in helping guiding us some of these processes and putting them into place. But thank you for your time. Any particular questions? I'm not going to have any issues in the area, so quite ahead. Thank you.